Hello friends, let's have a look at the review of a 2022 November question and do the unholy version of it. Okay, so let's get to it. So yeah, for this problem, it was a pretty nice, the fundamental theorem of algebra. And I want you to remember, if you have the complex root, yes, the conjugate is also a solution. And not only that, but also I want you to make sure that the, you don't have just a linear factor, but also you got a quadratic factor. So make sure you're always keen on working with the, if this is my complex root, I'm going to write as a z squared minus twice of the real part of the omega times z plus modulus omega squared. So, sorry, modulus of, sorry, the complex number here, this was omega. So yeah, that is the quadratic factor. So I always want you to think about that, right? And also, for polynomial, somewhat the coefficient of the second leading term is the, something with the parameters, and then something with the sum of roots of, right? So make sure that you're, the Vieta's formula, right? The alpha 1, alpha n is the negative an minus 1 over an. That's the ratio between the leading coefficient and then the one before. And then, there are many versions of it. There's a product version, the product of two terms, two roots, right? That will be the next one, right? So it's alternating, so plus a n minus 2 over a n. And you do this on and on and on. Alpha 1, alpha n, that will be negative 1 to the power of n. That's the alternating term, right? So the a naught over a n. So that is the formula to remember. So maybe this question was something to do with that. I'm not too interested in actually. But yes, I'm more willing to do the unholy version of it. So, whenever you're solving the polynomial, right? Whenever you're solving the polynomial, it's likely to work with the rational root. So you can do the rational root test. If the polynomial has a rational root, it must come in the form of what? Z is equal to, plus minus factor of the, the constant term. That's the rational root test, right? Over the factor of the leading coefficient, right? So that is what we do. However, in this case, as you can see, the constant term is a 1, and then the leading coefficient is 1. So the ratio of those factors can only be z being plus minus 1, you know what I mean? And if I actually plug it in, you can see that neither of them makes it 0. So none of them is actually a root. So I cannot find the rational root using this technique for this one, unfortunately. However, what I can do is to actually use the complex number, right? So this is a very popular question to work with the complex number. So let's get to it. So for this one, I want you to remember every time you see this polynomial of a symmetric coefficient, okay, every time you see the symmetric version of it, then I want you to think, oh, okay, so this is definitely checking with the following form. Z to the power n plus 1 over z to the power n is 2 cosine n theta is what the question is asking about, right? So that identity is going to be used here. So let's get to it. So here I can tell the z cannot be 0. Right? Because if it had been a 0, it would have been a root to make the left-hand side 0. It doesn't become. So I know it's not 0, so it's actually quite nice to divide. So what I want you to do is to divide both sides by the z squared. It's okay. This doesn't cause any trouble because it ain't 0. So that's great. So if I do that, then I get the z squared, and then 3z minus 2, 3 over z plus 1 over z squared is equal to 0. So what I'm going to then pair are the ones in the symmetric like that. So that's great. So then I'm going to have z squared plus 1 over z squared. So then I have a z squared plus 1 over z squared. And then I'm going to have plus 3 z plus 1 over z. And then minus 2 is equal to 0. Okay, so I'm going to compare with the one by the first and the last. And then I see if it's a square, then you see the term over there is going to be 2 cosine 2 theta. Plus for that one, it's going to be, 6 cosine theta. Minus 2 is equal to 0. That is great. Then now it became a trigonometric equation. So now I got the trigonometric equation with the even coefficient. So maybe I will reduce it further by dividing by 2 on both sides. So that is great. That becomes 1, 3, 1. And then, yes, this is almost good because I got the cosine, but I got the different multiple of the angle. Maybe I don't like it, so I'm going to use one angle in here. Double angle formula, but remember there are 3 double angle formula for the cosine. Which one do you think is going to be more suitable here? Yes, the one that has just in terms of cosine, please. So here, if you look at the first kind, I get the 2 cosine squared theta minus 1, and I get the, what is it, plus 3 cosine theta minus 1 is equal to 0 is what I have. And then what I can do here is 2 cosine squared theta plus 3 cosine theta minus 2 is equal to 0 is what I have, right? So that's great. So now I have 1, 2, 2, 1. I can factorize it plus minus. That is great. So for this one, now I see cosine theta is negative 2 or 1 over 2. But as you can see, for real value of the theta, this is not possible because cosine is bound by plus 1 minus 1. I got the cosine to be half, right? That is great. Then that's great because the sine theta by the Pythagorean identity will be plus minus square root of 3 over 2. Well, that's great. And oh, by the way, sorry, this would have worked if z was a cis theta, right? My bad. And here, yes, I'm letting the z to be the complex number, a complex number. So then I'm very happy because I already have the cosine and sine, right? Then I can find the cis form of it. Oh, that's not that bad, right? So that is great. So for this one, what I can do is to find a quadratic vector because remember, for this one, it suggests that the z will be given as, 1 over 2 plus minus I with 3 over 2. So complex root and its conjugate. So very great. And then we just established that if you have a complex root, then you can find a quadratic vector by using the formulas. It should have the quadratic vector of z squared minus z plus 1. So this one should divide that quartic polynomial. I'm very happy with that. So let's do that. So, oops. If I do that, let's do the long division here, my friend. I know it must divide because it's a factor. So if it did not divide well, that means my computation had been wrong. So make sure you get the remainder to be 0. So let's do the long division here, my friend. So I'm going to have z squared to match the degree. That is a great. Then I'm going to subtract. What happens here? Then it cancels out. Boom, I got the 4z cubic minus 3z squared plus 3z is what I've got, right? So then what am I going to put? I'm going to put plus 4z, right? So to match the coefficient. So that is a great. So then I have, 4z cubic minus 4z squared plus 4z. Voila. I'm going to subtract again. So then if I did, what happens? That one cancels out. That one has just z squared minus z plus 1. Then very good. So then I'm going to put just add 1 here to make the same term. If you subtract, it becomes a 0. Oh la la. Okay. Oh la la. Very good. I'm very happy with this. I'm very happy with this. So now I just verify that this is going to be another quadratic vector for that quartic polynomial. So that is great. So what I'm going to do is I'm going to factorize this. So that polynomial now is going to be factorized by that, and z squared minus z plus 1 is equal to 0. So it's a product of a quadratic vectors. Then I found this one already using the complex number. We already established that it's plus minus 1 over the plus minus root 3 over 2i. And that quadratic here, if I check with the discriminant, I get the 4 minus 1. It's a positive, so I'm going to get 2 real roots, but an irrational number. No problem. So if I use a quadratic formula, that's a negative 2 plus minus root 3. So I found the 2 beautiful roots are in real number, 2 roots in complex number, in total of exactly 4 roots in complex number. So whenever you see the symmetric coefficient for the quartic polynomial, it's very often to divide by the z squared and use the complex identity. Okay? Please remember this. Okay? All right, let's have a look at the trigonometry and functions. So yeah, I love this type of question. You know what I mean by that is it's not like a formula-induced problem. You know, for formula-induced problem, you just have to plug it in and just get the computation correct, right? But for this one, it requires the thinking, especially what it means by the function to have your inverse function. You need to pass the horizontal line test, and also not only that. You know, this is something to do associated with the reference angle and complementary angle. So you should be master of it, right? Meaning, so for example, if I have a cosine pi over 2 plus theta, for example, it's not that, but I'm just giving you an example. I know if I see pi over 2, it's going to be a complementary angle, so that the cosine must be in the form of a sine theta. However, I gotta be careful whether it's gonna be positive or negative. But it doesn't matter if theta is obtuse or acute, it applies the same. But if you just assume, okay, for your convenience, that theta is acute, then I send it to the second quadrant for cosine, which then makes it negative, because in the second quadrant only sine is a positive, isn't it? So it's going to turn out to be negative. So you should be master of this type of stuff, that we are able to rotate around in the unit circle and decide whether it's gonna be positive, negative, sine, cosine, or tangent. Okay, let me give you another one. So what if I did the sine negative 11 pi over 2 plus theta? Why not? But you know what? I know that this is gonna be complementary angle because I got the odd pi over 2. So whatever, I know it is going to be something with the cosine. I simply have to verify whether it's gonna be positive or negative depending on its location, you see? So let's rotate around first. So if I got the negative 11 pi over 2, that's almost negative 5 pi, isn't it? So I'm landing in here. But I'm gonna subtract by pi over 2 once again to make it as a negative 11 pi over 2. So I'm landed here. But I'm adding it, so I'm in the second quadrant. So what is the sign for the second quadrant? It's always positive, so I know it's gonna be positive. Like this, you should be master of this. So, and also a lot of a sketching problem here. I love this problem because, function, you really need to know how to sketch things without using calculator or even calculus. For example, you should know how to sketch things like this without using calculus or calculator vaguely. And we're gonna talk about that very soon. But yeah, let's have a look at the unholy version of the problem. Let's get to it. So yes, like I said before, you should be master of it. We just talked about the sine, cosine, and tangent also changes to cotangent if you do the pi over 2 minus theta. But yeah, then this was one of the, I think it was 2018 or etc. or something like that. To sketch this, it was a paper 2, but I'm saying that this can be well paper 1 problem also. Okay, so let's have a look at so here, yeah, a lot of people, when you wanted to sketch this function, a lot of people attempted this with the complementary angle, but it actually overcomplicates. What you should see is either you can simplify using the reciprocal, but it wouldn't help because it's going to be tangent over tangent with a different angle, or use the complementary angle. No one tells you this. You see, you should be able to see that. That's the deductive reasoning. I need to be able to find the hints using my existing knowledge. Am I going to use reference angle? Am I going to use a reciprocal? Am I going to use the complementary angle? Those thinking is required in general math. So let's have a look. So for this one, yes, cotangent pi over 2 minus x, sorry. If I let this to be theta is the same as who, my friend? You're absolutely right. So tangent, it's the tangent pi over 2 minus, it's pi over 4. It's the same angle. It's going to be pi over 4 minus x. That's great. So if I use the algebra here, actually you realize that's a 2 pi over 4 minus pi over 4 plus x. I'm very happy with that, you see? So that is great. That's lovely. So here, actually make it as a perfect square, isn't it? And yes, squaring a function, or square rooting it, or reciprocating, or things like that are the focus of the study of a function transformation. You're not going to be just learning, the translation, reflection, or dilation. You're going to be, playing around. And this can be definitely a paper 1 problem. And let's see how we're going to do this vaguely. So yes, you're absolutely right. What I like to do in order to sketch this function, not like at one go. You can do the series of a transformation. You know what I mean? So for me, if I had to sketch this one, I'd have sketched who first? X plus pi over 4 first, you see? And then, from the typical function, it's translated to the left by pi over 4. And his origin, his intercept from 0 is going to change to negative pi over 4. That's not a problem. But also tangent function, it's a rational function. You should know that it exists periodic vertical asymptote. So if I come up with the first 2 vertical asymptote, this would have been the plus minus pi over 2, right? But then now I have done the translation to the left by pi over 4 unit. Then the positive vertical asymptote is going to be pi over 4. And then the negative vertical asymptote is going to be who? Negative 3 pi over 4. That is great. And then, you know what? Before squaring it, I'm going to sketch the tangent function like this, you see? So that's great. And what I want you to do in the y-intercept, I got 0, 1, you see? And then what am I doing? And then I'm squaring it, you see? Then I'm going to square this. Yes, and there are going to be some squaring function here, square rooting it. But whenever you have those type of function, I think your standard point should be 1. Because, you know, 1 square is itself. But if it's bigger than 1, everything gets bigger. If it's between 0 and 1, if you square it, it gets smaller. So for my graph here, the part between 0 and 1, it's going to get smaller, you see? It's going to get smaller. But after 1, it's going to get bigger, you see? And then the negative part will be just positive. So that is going to be the shape on the first interval of the vertical asymptote. But of course, it's a periodic, so you're going to have multiple shape like that. But what I'm trying to do here is, yes, the question number 8 on the November 2022 was something to do with the function and sketching with the trigonometry using the reference angle or complementary angle. This also, well, can be extended like this with the unholy version of this, okay? So keep your business clean, my friend, with the trigonometry. It's a very, very important chapter. Yeah, and then, yeah, like I said before, you know, you're going to look at a lot of inverse function also. And then, you know, for finding the inverse function, if it's already 1-to-1, it's easy peasy, lemon squeezy, because it's like the exponential, you know, its inverse is going to be logarithmic, vice versa. Rational function, linear function, those one-to-one function already has inverse. It's pretty easy to find. However, a function like this may not have the inverse. So what you need to do is restrict the domain, isn't it? So those things we got to be careful. But this will be assessed to 2 parts. For what values of x is a one-to-one function to restrict so that it becomes a one-to-one. And then what is the inverse function expression? You know, this is also a very popular form. So let's get to it. But what I want to do is to talk about sketching of it, right? So I want to sketch this without using calculus or calculator. And for that, you know, what I would suggest is that you sketch who first? You know, let's go with the reciprocal version of it, which is x squared plus 1 over 3x. This is the rational function. It's in the syllabus. You get to learn the horizontal asymptote, slanted asymptote, and also the curved asymptote. So for this one, if I do the long division, I get the x over 3 plus 1 over 3x. I'm very happy. If you send x to infinity, this will diverge in a way with what? The linear function. That is very good. I'm very happy with that. So on the xy axis, my friend, what I'm going to do, every time you sketch the function, please indicate who as a priority the asymptote place, because it gives you the general behavior. So now I got the vertical asymptote is x equal to 0, obvious, because the denominator cannot be 0, right, oh my friend? So now I got the x equal to 0. But here it's not the horizontal asymptote, please do not be fooled. This is a slanted asymptote, this is the oblique asymptote of the x over 3. So I'm gonna sketch the x over 3 like that. So that is brilliant. But if you look at the function in general, yes, finding the intercept is key. But you know, x squared plus 1 cannot have real root, so I don't think I'm going to have the x-intercept. But on top of that, you know, on this type of linear function for positive x, I'm adding something on it, isn't it? So my dots should be above the x over 3. But for the negative x, on top of x over 3, I'm subtracting, so it should be below. So it is very common to realize the function is going to be like that, like the Nike, okay? And then what do? I'm going to do the reciprocal transformation. To get the fx, you realize, I need to do the 1 over gx. I need to do the reciprocal transformation. And this is also very popular for the function transformation, isn't it? So what I'm going to do also is that from the vertical asymptote, what am I going to do? I'm going to put the x-intercept of the, the reciprocated function. So I'm going to, this vertical asymptote now becomes the x-intercept, right? Very good. And also increasing behavior, we change to increasing to decreasing. And also think about this, you know, for my original function gx, as x gets large to the positive or negative direction, they diverge. But if you reciprocate 1 over infinity, we assume that it will converge to 0. So it has the horizontal asymptote. It has the horizontal asymptote. That is great. And it goes, it went down and up, but now the reciprocal transformation, when the denominator is getting smaller, the fraction itself is going to get bigger. So it's going to go up and down. But obviously it depends on the scale, right? For that precise moment of that maximum minimum, you need to use the differentiation to find the local maximum minimum and then compare if it's should be above the 1 or below the 1. But I'm just sketching roughly. Okay, so it's just a rough sketch. It gives you the idea. So this is a very typical shape of a function. There are many functions to memorize of its shape, and this is one of the popular ones. So if I have ax over x squared plus b, where a and b are positive, the shape looks like this. But you should not only memorize, but also be able to derive using the reciprocal transformation. There are many kinds that are popular for the exam, like the x times square root of 1 minus x squared. It's got the interesting shape like that. Okay? Another one also that is popular. Who is popular? I think these two are popular for the paper one, especially with the differentiation, because as you can see, it uses the quotient rule, it uses the product rule and chain rule, so obviously they are popular. Okay. So as you can see, if you want to have inverse, it depends on your choice, right? You can either, restrict between the local minimum, local maximum of the reciprocal version of it, or away from those maximum minimum. So if I let, for example, this to be, it's odd function. So here, if I call this as a negative a, and this is a, the inverse function would exist between, negative a to a, or you could have said also what? X is less than or equal to negative a, or x is bigger than or equal to a. So those intervals will definitely give you one-to-one function, hence has the inverse. And those are that's the way we typically talk about whether it's going to have inverse or not. Okay, I do have inverse, and I want to find the actual inverse. And for this one, sure, it did not have inverse initially, so even if interchange x and y, you might not see the expression of the inverse right away. So you might actually have to use some formula to derive it. So let's have a look at this. So for those typical non-one-to-one function, interchanging x and y does not give you the answer right away. You need more steps to find the solution. So here, if I interchange x and y, this is going to be x is equal to 3y over y squared plus 1. If I do the rearrangement, I get the xy squared plus x minus 3y is equal to 0. So now I'm trying to find the solution of a y in terms of x, and then the equation now is in the form of a quadratic. That is great. That is beautiful. Whee! Sure, but I'm going to rearrange so that it's in descending order with the expression of y. So I got the square and then the linear. That is great. Now I get a quadratic expression. I want to solve the y in terms of x. So my variable here is y. The rest are just constant coefficient. You can think of it like that. So now I can use the quadratic formula. That is great. So let's use the quadratic formula. Y is equal to, if he's going to be my b, so it's going to be 3 plus minus square root of 9 minus 4x squared over 2x, my friend. I'm going to call that as my inverse function. So that is great. But here's the thing. Yes, you're right. The inverse is supposed to be unique, my friend, right? So I cannot leave like that. You need to decide whether it's going to be positive or negative. But here's the thing. Sure, what you also need to do is to rely on the domain of the original function. So because we said this function can be one-to-one if it was between negative a and a, or this function will also be one-to-one if it was away from, right? So depending on this domain, you can decide whether it's going to be positive or negative. So you must not leave the expression of the inverse as the ambiguous case because it needs to be unique. Understood? So please rely on the initial domain to decide the range of the inverse. All right, that's great. So this is the question number 9, something with the differential equation, and this is a separation of variable, right? Is it separation of variable? No, it's not, because rearranging that to the other side, it still has the x and y, and this is a typical homogeneous case, right? And for this homogeneous case, yes, it's very typical to divide by, in this one, yes, I would divide by an x squared, why not? On top and bottom. So what you see there is that I got the y over x squared minus 2 over y over x. And I'm done, right? So then what you can do here is to let the y is equal to vx. And then this is a typical method of working with the homogeneous equation, right? So then dy over dx, I want you to memorize. I don't want you to do the product rule. This should be embedded in your head. dv over dx times x plus v is going to be the substitution, and make sure the homogeneous case is just the case, homogeneous equation is just one more step to make it separable. So whole point here, if you make the substitution there, will then yield the separable case. So you can solve it. But what I want to talk about is the unholy version of it. So a more challenging form of the separation of variable will be the following. So imagine I wasn't given these hints, you see. In that case, if you look at the right-hand side, it's neither separable nor homogeneous case. I cannot put the dy over dx in this form at the moment without the hints as the function of y over x. Because even if I try to divide by the x, I got the unwelcome guest of the constant. I will end up having a 7 over x or 1 over x, and maybe I don't want that, you see. But instead, yes, you're absolutely right. What I want to do is to use the given hints. You see, it's to get rid of the constant. So they are trying to solve the simultaneous equation, you see. So if you plug it in on the right-hand side, let's just plug it to the right-hand side. So this is the unholy version of the homogeneous equation when it's not obvious to get rid of the constant, but I'm given a hint to get rid of the constant. So let's make the substitution. If I let x minus 1, y to be y plus 3, you end up having minus 4, minus 3, plus 7 gets 0. So on the right-hand side, that's going to be just typically 4x minus y. But I want you to notice I wrote it in capital letter, so that's great. On the denominator, that's going to be 2 capital letter x plus capital letter y. And my job is to then to integrate this, so you can't use the left-hand side alone because that's a lowercase. I got to have the capital letter y, capital letter x on my derivative expression. So for that, let's have a look. So for my given variable substitution, I was given x is equal to capital letter x minus 1. All right, so let's differentiate with respect to what? What do you want to differentiate with? Very good. I'm going to differentiate this with respect to capital letter x. Why not? So that gives me, okay, so the left-hand side is going to become who? If you differentiate with respect to capital letter x, on the right-hand side, it will be just the 1 because that's the linear function. Okay, so this suggests that dx is going to be d capital letter x. All right, that's great. And you can do the same thing. You can do the same thing similarly, right? If you let the, dy over dy, and this time you're going to get also 1. So this will suggest that the dy is equal to dy of the lowercase and the capital letter. So very good. So then what you can do actually is to realize if you do the division of that, considering the derivative like a fraction, this little cheating, okay? But I end up having that, right? So it's actually becoming who? That differential equation now becomes dy over dx. And then is equal to who? 4 capital letter x, capital letter y, over 2 capital letter x, capital letter y. So that is great. Now it became separable because you can do who? Yes, I can now divide the capital letter x, capital letter x. So this becomes now 4 minus y over x over 2 plus y over x. Voila, that is great, okay? That is great. But here's the thing, yeah, you're absolutely right. Then you can solve it using the substitution, but this time I'm going to let y is equal to vx like that, right? And then you can solve solutions for capital letter y in terms of x. However, you're absolutely right, you got to bring it to lowercase. Okay, and that is how it's going to be. So this has actually multiple steps because you got to solve for the capital letter and then bring it down to capital lowercase using another substitution of that. So, you know, I encourage you to try. But for this one will be the more advanced version of the question for the homogeneous equation. Okay, that's great. Yeah, you know, this question is also beautiful because it asks you to sketch the function, you see. So every time you're sketching the general function, what you need to do is to work with the sign diagram. Because, you know, what you want to do is to find dy is equal to, so you want to sketch this. And then the very first thing I want you to do, my friend, is to find the stationary point and then the second derivative being 0. I want you to notice that I didn't call it inflection point because you need to check the sign. And then you're going to draw an extended, table of the of the sign diagram. And then use its table to talk about whether it's increasing, decreasing, and then talk about the general shape. But beforehand, my friend, whenever you are working with the function, if it has the existence of the vertical asymptote or the horizontal asymptote, you must indicate them first. Okay? So that's going to be the first thing that I'm going to talk about as an unholy version of this problem. But the second unholy version of the problem is sketching with the absolute value. Every time it's got something absolute value, or it's solving with the inequality with the absolute value. For example, for this one, I don't want you to square it. That will be very silly. Please sketch. So learn how to sketch with the absolute value function, my friend. So let's have a look. So I want to sketch this using calculus on paper 1. However, yes, it's got a bunch of the exponential function, doesn't it? And therefore, I can see that I might have the horizontal asymptote. You must realize that every time you are sketching a function, check its domain, check its horizontal asymptote or vertical asymptote. For this one, voila, I do have horizontal asymptote, so I'm going to sketch as what? Oops, sorry. I'm going to indicate, so as, x goes to negative infinity, y is going to 0, so I do have a horizontal asymptote. That's great. Before derivative, indicate that first. That's the function understanding. Now the calculus understanding is going to involve with the derivative. And for this one, if I have to sketch, I know in my head I got to find foo first. dy over dx being 0, and then second derivative being 0. I'm going to solve that first. So let's dig in for this problem here, my friend. So I'm going to let what? The second now thing will be finding the stationary point. And please remember the derivative, a to the power of x. If you differentiate that, it's a to the power of x ln a. That is great. So I know for my derivative here, first derivative will be 3 to the power of x ln 3, oh la la, minus 2 to the power of x ln 2 is what I've got, isn't it? And then, this is going to be 0. I'm going to let this. So then I know if you let them to be the same, 3 to the power of x over 2 to the power of x is ln 2 over ln 3. Okay, so then I have a 3 over 2 to the power of x is log base 3, 2. Well, that's a bit tricky, right? I gotta use the calculator. Okay, so maybe it wasn't a good choice of the base because I want to talk about the paper 1 version of it. So what I would suggest is maybe I'm going to make it as let's say 9 and 3. How about that? I'm gonna make it as a 9 and 3. Okay, so let me just change it so that I can talk about with just without using a calculator because I want to solve it. So here, let me try to differentiate once again. Sorry. So dy over dx is 9 to the power of x ln 9 minus 3 to the power of x ln 3. And I want to solve this to be 0 for finding the stationary point to talk about its monotonicity, increasing, decreasing, possible maximum, minimum, or inflection point. So let's see. So I want to solve it. So if I want to solve it, I will do the rearrangement here. No problem. So if I just let this to be the same, and then, then you're going to rearrange. So this is 3 to the power of 2x divided by 3 to the power of x will give you the yield 3 to the power of x. That's great. Then I got the ln 3 over ln 9. I hope that you are able to solve this quickly, simply just half, right? Then, yeah, I can solve it. So x will be, log 3, 1 over 2, right? And then would it be positive or negative? Very good. It should be negative, right? Because what is it? The inside of log that's between 0 and 1 that makes the log negative, right? That is great. Okay, that's my stationary point, all right? And then before doing anything, I'm going to find the second derivative being 0. Okay, let's do that. Why not? So that's going to give me, what is it? It's going to be 9 to the power of x, but this time ln 9 square minus 3 to the power of x times ln 3 square is equal to 0. That's great. So if I do the rearrangement to solving it, then I get 3 to the power of x is ln 3 over ln 9 square. So that's, what is it? 1 over 2 square. Okay, that's great. So it's going to be 1 over 4. Then I have x to be log 3, 1 over 4. That's also negative. Okay, that's great. And who is smaller? He's smaller because it's oh, sorry. Is it smaller? It is smaller because it's closer to 0. So in the log function, we know that 1 over 2, 1 over 4 is going to give you the y value like that. All right, that's great. Okay, so, and I want to use it. So how am I going to use it? The stationary point here was log base 3 half, and the second derivative being 0 was x equal to log 3, 1 over 4. And then what I want to practice here is every time you're working with the sketching of the function, you need to make sure to use the extended sign diagram, not just the first derivative, but also the second derivative, so that you can talk about the concavity as well as the inflection point. So what I'm going to do is x, f prime, f double prime, and then the f. And then, yes, what's the single most important in function? The domain. I have the difference of the log exponential function 9 to the power of x, 3 to the power of x, and its domain is all real. So it can come from the negative infinity, no problem. And I'm going to indicate those two the crucial points that we just found on the way. And who was smaller? I'm going to call it x2 and x1, and x2 was smaller, all right? x2 was smaller, so it's going to be towards to the left. So I'm going to write yes, I'm going to write as x2 here. And then I'm going to do the neighborhood, and then the x1, and then neighborhood. Remember x1, I call it as a log 3, 1 over 2, which is negative, so both of them are negative, so maybe it's good to indicate the 0. And then boom, boom, boom. But he's insignificant, right? He's neither first derivative being 0, nor the second derivative being 0. Okay, so that's great. So for the first derivative being 0, there's only one point there, which was x1. Okay, and my job is to indicate how the sign is going to change. So my first derivative was this. And yes, maybe it's a good idea to factorize to solve either positive or negative around his neighborhood. Okay, so maybe I would factorize this by, 3 to the power of x ln 3, why not? So then I'm going to have 3 to the power of x ln 3, just like that. Minus 1. So that's the factorized version, right? And I don't have to sweat too much on this part because that's just exponential, right? So that I know it's going to be positive always, no matter what the x value is. However, on that one, it depends on the neighborhood, you see. My stationary point, x1, was given as log base 3, 1, 3. And I want to make sure on the neighborhood who is going to be positive, who is going to be negative. So then I'm going to choose slightly smaller, slightly bigger value, but you need to make sure that value is smaller than x1 should still be bigger than x2 because that's another point that I want to check. Oh, never mind, because it doesn't give you stationary point. So why not? I'm going to put that value on my derivative to check whether positive, negative for the first derivative. Let's do that. So for the first derivative, if I put log 3, 1 over 4, my friend, what do you get? If I plug into the base of the derivative, here. So I don't need to worry about that. That's gonna always give me positive no matter what x value is. So for that one, it's gonna give me 3 to the power of my friend, log 3, 1 over 4, ln 3 minus 1. But if you check that, right, that it will come out just a 1 over 4. So it's a 1 over 4 ln 3 minus 1. Where 1 on the base of log is gonna be ln e, isn't it? So what you're looking at here is ln 3 to the power 1 over 4 over e, okay? And what I think is this is going to be a lot smaller than 2, isn't it? Because it's 3 to the power 1 over 4. You're looking for a number that you multiply 4 times to get 3, and it's going to be pretty smaller than 2. You can compare. You can put it into the power 4. This is obviously a lot bigger. So this itself is less than 1. Bigger than 0, so this is going to be negative. So I know in that neighborhood it's going to be decreasing, and you can do the same thing. Now I had the stationary point with the 1 over 3. Maybe I would put the log 3, 1 over 2, which is still negative but bigger than the x1. If you do the same procedure, you're going to end up showing that this actually becomes positive. So now I have increasing, decreasing behavior. That is great. Now I'm going to move on to the second part here, where x2 is the log 3, 1 over 4. If you put it into the second derivative, that was a 0, but that does not give you the inflection point right away. What you need to make sure is to check its neighborhood, whether it's going to be positive or negative, right? Sure, so now, then that I will do using the second derivative, of course, and yes, it would be maybe nicer to factorize. So what I'm going to do is to factorize by 3 to the power of x ln 3 squared as a common factor. Then what I'm going to end up having here is going to be, that's 3 to the power of x. That is great. Ln 9 squared is 2 ln 3 squared. So that's going to give me 4 ln 3 perfect square. That's great. And I'm going to subtract that by, what is it? 3 to the power of x ln 3 squared. Okay. Is it? Give me 1 second, my friend, because I'm supposedly factorizing that by ln 3 squared, my bad. So I shouldn't have this, right? Yep, I shouldn't have it. And then that should be simply 1. Okay, so yeah, that's good. So I have that, right? That's what I have, isn't it? So let me quickly double check. Yeah, that looks great, right? So that's great. So I know if I put that, that makes it 0. Then I want to check its neighborhood. You know, who do you want to plug? So anything smaller. So maybe I would put on this neighborhood, I'm going to choose log base 3, 1 over 5. You know, why not? So if I put 3 to the power of log 3, 1 over 5, 4 minus 1, you know, then I get, what is it? 1 over 5 times 4 minus 1, which is negative. Okay, so then I know it's going to be negative there. And if you put log 3 1 over 2, that gives you 1 over 2 times 4 minus 1, which is 2 minus 1. That's a positive. So it's going to be positive here. Oh, hold on a sec. So now I got all the beautiful values for my beautiful sign for my first derivative and second derivative to perform the sketching. So what I'm going to do is this. Okay, whatever we do, whenever there is an asymptote, that's the first priority to sketch. For this one, we had the horizontal asymptote of y equal to 0. That is great. And then I'm going to indicate those significant points. And yeah, you know what? Actually, it would have been better for me to sketch the y-axis towards to the right a bit, because all those stationary points that we had were, and then the second derivative being 0, both of them negative, so maybe it's better to indicate here. And then, you know, I'm going to put x2 and x1 around here. So this is going to be x1, and this is going to be x2. Okay, and then for sketching, you need to put those values on the function directly. Okay, so now this was log 3 1 over 2, wasn't it? Yes, it was. And this was log 3 1 over 4. Now to indicate on the function, you need to put it onto the original function. So for example, if I put the x1, 9 to the power of log 3 1 over 2 minus 3 to the power of log 3 1 over 2. So let's indicate the value. So that is going to just give you half, isn't it? So that's great. On the first one, that's going to be 3 square log 3 half, isn't it? So that's going to be 1 over 2 square. So that's a quarter. So you now know that that's going to give you a negative quarter. So that at x1, I'm going to have negative quarter. So it's going to be x1 comma negative quarter. So that's great. And let's try to plug the x2 on my original function. So if I put the x2, which then becomes 1 over 4 inside, what am I going to get? Let's see. So it's going to be, let me erase that. So it's onto the original function, right? Don't get it wrong. So 3 to the power of 2 log 3 quarter minus 3 to the power of log 3 half. Sorry, quarter. Okay, so that's great. So that's gonna be 1 over 16 minus 1 over 4. That gives me negative 3 over 16, which is slightly bigger than negative quarter, because negative quarter in the common denominator with the 16 makes negative 4 over 16, which is smaller. So I'm going to indicate slightly bigger here. That is great. And make sure, yes, you need to check with the general behavior. I know up to x1, things are going to be decreasing. And then after x1, it's going to have a turning point. It's going to go to increasing. Then yes, like I said before, maybe it's good to indicate the y-intercept if it's possible. Yes, it is possible to have y-intercept. If you put 0, 0, that's 9 to the power of 0 minus 3 to the power of 0, which makes it 0. It's a 1 minus 1. So then I need to pass the origin, so it's going to go up like that. However, yes, you are not just checking on the monotonicity, but also you need to check with the concavity, the shape of the function, and do not disregard the horizontal asymptote. I need to show my behavior coming from the horizontal asymptote. In fact, from the x2 over there, things were concave down. So while decreasing, concave down must be portrayed on the graph. So for me, what I'm going to do is to coming from the, what is it? Horizontal asymptote, but concave down. So the shape is going to look like this. But after that point, still decreasing, but concave up because it's the inflection point. Okay, that is great. That is brilliant. But after x1, because it's a turning point, it must go up, but then it must pass the origin. So things are going to sketch like this. So it's roughly speaking, so it's going to come from the horizontal asymptote, go all the way up. It's going to be the function like that. The reason I'm showing you this, yes, whenever you want to sketch, you need to use the table, sign diagram, the x derivative, second derivative, the function. But also, you need to indicate what the asymptotes are like. For the exponential function, I know there's horizontal asymptotes. I must indicate is one thing. Okay. Oh, okay. So another function that is very popular to sketch is this function here. So yes, I talked about the horizontal asymptote from the previous example. I gave you this example because this is to associate with the slanted asymptote. So for the slanted asymptote, sure, we saw with one of the examples was if I had x squared plus 1 over x, if I do the long division, I see x plus 1 over x, and it's obvious for me to spot the horizontal asymptote here. However, if you look at the arctangent, if you want to see his behavior, you will send x to positive infinity. Then yes, the x is going to diverge, right? Because it's a linear function. But if you look at the arctangent x, if you send x to positive infinity, it converges to pi over 2. So in fact, yes, my function does diverge. I'm not saying it converges, but diverges linearly eventually by the x plus pi over 2, which then means it's a slanted asymptote. So for him, it's actually an interesting function because it has two horizontal asymptotes, my friend. So yes, this is the slanted asymptote as x goes to positive infinity. So can you guess when it goes to negative infinity, what's going to be my horizontal slanted asymptote from that function? Sure, x still diverge, don't get me wrong. However, for the arctangent x, if you send x to negative infinite, it converges to negative pi over 2. It converges to negative pi over 2, like that. Okay, so that's great. So now I'm going to indicate two slanted asymptotes before doing anything. Before doing any differentiation of the first derivative or second derivative or any x-intercept, y-intercept, no matter what, indicate the asymptotes first. So I'm going to indicate the x plus pi over 2 and x equal to negative pi over 2. So that's what I'm going to do. And then x minus pi over 2. And then, the behavior of the first derivative being 0, second derivative being 0. Talking about the monotonicity and concavity is your job. But what I'm trying to say here is whenever you're trying to sketch the function, make sure you indicate asymptotes possible, if there is. Okay? Obviously, if it was a polynomial, you wouldn't bother, right? Because it wouldn't have the asymptote. The second part of the question number 10, what's so beautiful about it was it involved with the inequality with the absolute value. Please, every time you have absolute value, I would strongly suggest you to sketch. Okay, you must sketch, do not square it. That's not the spirit of the problem. So if you look at the first problem here, I'm doing the unholy version of the problem, right? So for this one, yes, before I do anything, I would sketch the typical function first. The original function, let's claim that this is the exponential function, and that's pretty straightforward for us to sketch. It's got the horizontal asymptote of u. Very good. It's got the horizontal asymptote of a negative 2. So I'm going to indicate y equal to negative 2 just like that. So that is a great, right? And it's going to be an exponential growth with the y-intercept of negative 1. So I'm going to sketch my function like this. So I got the e to the power of x minus 2 with the y-intercept of 0, negative 1. And the x-intercept is, ln 2, 0. That is great. That is brilliant. However, the reason we sketch this is to solve this inequality. And yes, I want you to tell me, my friend, what happens if you put an absolute value on the outside, on the range? You're absolutely right. You will make a reflection along the x-axis. All the negative becomes positive. So is the horizontal asymptote. That negative 2 now will be shifted up by the horizontal asymptote being y equal to positive 2. And then that one would go towards to the end like that. So that is the reflected version. If it was a positive already, it's going to be the same. I don't bother. But what about the absolute value domain? People often make mistake with the absolute value outside. That one make things symmetric from the right along the y-axis, right? So what I'm going to do is I'm going to get rid of the left part here, isn't it? Then I'm going to, make it symmetric from the right-hand side. So it's going to be, what is it, my friend? Yes, it's going to make it symmetric from the right like that. So that is going to be my function if it had been the f of absolute value domain. So what you need to do is disregard the left, because you can't have the negative input because I'm making everything absolute value being positive. So whatever the y value will be flipped along the y-axis. So for the right-hand side, if I sketch my friend with the, which color should I do, man? To distinguish, maybe I would do black. Okay, let's go with black color here. So the right-hand side will be reflected, you see? So that's gonna be f of absolute value of x. Obviously, the right-hand side is the same. So now, look at this. All right, so I'm solving inequality, and I need to indicate the region where the absolute value outside is bigger than the absolute value domain. So it needs to be above. So the absolute value outside was the blue function, isn't it? So the time he's above is going to be only this part. That's it, right? That's going to be his only part, right? So for that, I need to find the intersection. You're absolutely right. So for that one, x-intercept is a common point, so that's a one solution already. But I got to find the second solution here by making a piecewise function. The absolute value function, my friend, is another form of the piecewise function. You're absolutely right. So if I let this to be the first function to be absolute value of e to the power of x minus 2, that's going to be piecewise function. It's going to be just positive ex minus 2 if x were bigger than or equal to than 2. It's going to be negative e to the power of x plus 2 if x were less than 2. And as you can see, I'm trying to find the intersection on the left, right? So it's going to be the left piece, isn't it? That is great. If I try to derive the second function, e to the power of absolute value of x minus 2, it's going to be also e to the power of positive x minus 2 if x were bigger than or equal to 0. And it's going to be to the power of negative x minus 2 if x were less than 0. So that is great. Then obviously it's also to the left where the intersection happens. So for your equation, what you want to do is to just, associate with what, my friend? The left pieces only, right? I only need the left pieces. So that's great. So let's see. So what I'm going to do is let this one be the same as with that one, right? So that's great. So I'm going to solve an intersection with the exponential equation. So let's do that. So I'm going to let those to be the equal because those are the left pieces of the piecewise function with the absolute value function transformation. Okay, so then let's move here. Then it's going to be e to the power of x, boom, minus 4 plus e to the power of negative x equal to 0. What do you smell? Rock is cooking, yes. I see the exponential function is cooking. I see the quadratic function is cooking. You smell, okay? I don't think you will get the reference, do you? Because it's sorry, never mind, too old. So yes, now I don't like working with the negative power. So what I want to do is to make a positive power by multiplying with who, my friend? You're absolutely right, by multiplying e to the power of x. E to the power of x, just like that. No problem. And I'm going to do term by term. So that's going to be e to the power of 2x minus 4 times e to the power of x plus 1 is equal to 0. Then yes, now I see this is sort of a quadratic expression with the substitution of a t is equal to, for example, e to the power of x. This will then yield t squared minus 4t plus 1 is equal to 0. That is brilliant. So what you want to do here, my friend, is to use the quadratic formula. T is equal to who? 2 plus minus 4 minus 1. The 2 plus minus root 3 is the, let me write better actually, sorry about that. 2 plus minus root 3 is the e to the power of x, and I'm trying to find the exponential, the x, right? So let's put a log on it. So I'm going to get, what is it? Ln, the x is equal to ln of 2 plus minus root 3. That is a great. However, yes, I want you to notice this intersection happens as a 1 point. But I got two solutions. Maybe I don't like it. Are they possible? Yes. 2 plus root 3, 2 minus root 3, both of them are positive. So it's within the domain of log. That's okay. However, yes, my x value, the intersection is negative. You see? So then I need to have a negative value. So for the log, if it had been 2 plus root 3, that is bigger than log 1, which is going to be positive. So I need to find the value that is between 0 and 1. That's likely to be who? With the 2 minus with the square root of 3. So that is going to be my solution. Okay, so therefore, how are you going to solve the inequality? Yes, the x is going to be, bigger than, what is it? Ln of 2 minus root 3, and less than who? Ln 2 is going to be the precisely the solving inequality with the absolute value. Every time you see absolute value, please do not hesitate to sketch. Okay, for this one, yes, for me, it's very likely to working with the rational function. So I'm gonna sketch the rational function first, isn't it? So this typical rational function with the vertical asymptote and horizontal asymptote, those are going to be the main thing for me to sketch. The vertical asymptote is -3, horizontal asymptote is going to be y is equal to 1. That is a great, if you look at the y-intercept, that's -2/3, and then x-intercept is a 2. Boom, yeah, okay. But remember, I'm trying to solve with the absolute value domain. That is something with the sketch, my friend. So what I'm going to do is what? I don't care about the left side here. So I will get rid of it, you see? And then I need to make it what? Symmetric from the right-hand side. Then, my friend, is going to be the sketch of this absolute value rational function, isn't it? And I'm trying to compare it with what? A y equal to 2. And then who needs to be bigger? Yes, I wanted this constant function to be bigger. And you're absolutely right. He is always bigger than this rational function. That's actually quite marvelous. So you're going to say this is true for all value of x. Is what I'm going to say. Okay, this is going to be true for all value of x. So, whenever you have absolute value, it's either with the outside or inside. Please do not hesitate to sketch. All right. Oh, okay, love it problem here. So it's working with a lot of a complex number and then the composition, right? So do not, hesitate to composite this, to simplify the left-hand side, right-hand side, and see if you can do. And of course, this induction hypothesis will be, the result to prove will be solved with the hypothesis and this identity. So it wasn't that bad, actually. It was not that bad. But of course, I want to do the unholy version of question number 12. So let's get to it. So yes, for the complex number, I want you to be always keen on finding the argument. And the thing is, people often make mistake with this. Look, let me have a look. So imagine that this was a paper 1. Imagine that this was a paper 1 and you had to find the exact argument and then tell me if I'm doing right or wrong. And I say, oh, okay, so we learned if z was a plus bi, then let's call the argument of z as a theta, then we learn tangent theta is a b over a. So I say, okay, so his argument, if I let this to be also theta, then I should have a tangent theta being 4 over -3, which is -4/3. So I'm going to say theta is arctangent -4/3 is my argument. It's a very, very popular, a very popular mistake. This is wrong. Please do not do this, okay? This is wrong. Why is that wrong? It's because it didn't respect the inverse function. Remember, arctangent, right? His range is defined from -π/2 to π/2. Precisely, he only covers what? Yes, the first quadrant and then the fourth quadrant. It only covers positive acute or negative acute. And for the complex number, please grow accustomed to simply indicating on the Argand diagram. What I mean by that is -3 plus 4i. So it should lie in the second quadrant, but none of the inverse value of the tangent will get me the arguments. So you cannot actually get it as a simple arctangent. You need to rotate around. You need to do the reference angle, please. Okay? So what you can do here is, I will find the standard angle, which was arctangent 4/3. So if it's positive inside, I know it's a positive acute, but I want to send to the second quadrant using the reference angle. So for this argument, yes, as you can see, I need to send it to the second quadrant. So how much would you go? I'm going to go pi much, and then subtract by the positive acute, which is arctangent 4/3. Okay, so that is how you work. So please do not rely too much on the inverse function, because often leads to the mistake if you had to find the argument of the second or third. Inverse of the positive or negative for the arctangent, for the tangent is going to be only for the positive acute or negative acute. So please be careful. Okay, and then the second thing is, yes, this is also very popular. All right, so the cis theta times cis phi is who? you're right, it's gonna be cis theta plus phi. I get it. However, yes, you should know the sum. Please memorize it. Please memorize it. I've been saying it for a long time, and then right before the exam in May 2022, I uploaded some formula that people should memorize, and that came up on the paper one very nicely. You know, we explained that on the video, so you can check it out. So please remember, cis theta plus cis phi, you should know how to prove it by using trigonometry or vector, okay? So that one is going to be 2 cosine theta minus phi over 2 cis theta plus phi over 2 is what I've got. That's great. And then if I want to find the argument of it, right, so then I know omega is a cis theta. So omega plus 1 is the same as what? Very good. Cis theta plus cis 0. Please remember, 1 is simply cis 0 or cis 2 pi, but of course we prefer the smaller the better. Then I'm going to simply use this formula right away. No problem. So this is going to be 2 cosine theta over 2 cis theta over 2. Using that identity. Difference over 2, sum over 2. Oh, hold on a sec. So it gives you argument right away. So you don't need to sweat. Okay, so argument of the, what is it? 1 plus omega will be simply theta over 2 if omega was cis theta. So please also remember this formula. I cannot emphasize further. Okay, and also, yes, you know, there are many identities to memorize. Sum of arcsine, arccosine is a complementary angle, pi over 2. So is the arctangent x plus arctangent 1 over x. You should know how to prove it as well using the right angle triangle. Just make a rectangle, my friend. Then you realize that if I had the theta here, and that this is going to be pi over 2 minus theta. For example, if I let this a and b, then you know tangent theta, you know, b over a, and you can prove it using the, you know, the triangle number 1 and number 2 and add them together. No problem. Yeah, or you can just composite, you know. Then tangent pi over 2 is undefined, so very likely that you're going to have the denominator being undefined. That's that. But please remember this inverse trig identity is also very popular. And then also learn how to simplify the composition between the function and inverse function. Right? So for example, you know, we mentioned about it, we talked about it before, right? So if I want to simplify this, right? If I want to simplify this, oh, sorry, arctangent, yeah, supposed to be arctangent, my bad. So let's go cosecant arctangent x over 2. So imagine that I want to describe it as a t, you see? Imagine that I want to describe it as a t. So I want to let this to be theta, okay? Then sine theta is going to be simply 1 over t. Yes, for these things, you know, you can use Pythagorean identity, I don't mind. Personally, I like it, but I think for me, more intuitive is to use the right angle triangle. So I'm going to let this theta, and then the hypotenuse is t, you know, the opposite is 1. So then the adjacent is going to be square root of t squared minus 1 using the Pythagoras theorem. That is great. But here's the thing, you know, I want to get the, what is it, the, let's say I want to get in terms of, I want to get for the x. So, you know, who do you want to, for example, composite by, right? So this theta was the arctangent, what is it, x over 2. So it's probably better to composite by the tangent, isn't it? So if I do the tangent theta, which is tangent of arctangent x over 2, will be simply just x over 2, right? Because it's a function composition with the inverse function. On the right-hand side, with the right angle triangle, I get 1 over square root of a t squared minus 1. Okay, then if you flip it, then I get square root of a t squared minus 1 is a 2 over x. But my job is to simply get the t, right? That's the expression that I wanted to get in terms of x. So what I can do is to find a solution for t. I'm going to square it. So it's going to be t squared minus 1 is 4 over x squared. Therefore, t is going to be 4 plus x squared over x squared. Aha! So t squared, my bad. So t, which is the answer that I wanted to get, will be square root of 4 plus x squared over x. So that is also the way we can do. So yeah, I think, you know, converting around with the composition between the function inverse function is very popular. So please do remember. Okay. And yeah, you know, I think the question number 12 of November 2022 was to work with the sum of the inverse trig, and it wasn't that bad because you actually you were given the identity. You were given the identity of arctangent something plus arctangent is equal to arctangent blah blah over blah blah. So when you were moving from induction hypothesis to the result of proof, it wasn't that bad. It was well connected. However, the sum of the trigonometry is also very popular with the induction problems. And for this one, I want to discuss a few more things. So I'm not going to go over the basic step, but let's talk about the result of proof. Induction hypothesis implies the result of proof. So suppose this statement is true for K. So I'm going to just replace the n with the K. All right? And then my job is to show that up to what sign. So be careful if you replace with the K plus 1, it's multiple of 2. So you got to keep the linearity. So it's going to be 2K plus 1x is going to be the same as what? 1 minus cosine 2K plus 2x over 2 sine x. So that's my result to prove. That's my answer. I want to get there. However, I cannot use it. It's the result I need to show. I cannot use the result. But yes, as you remember, for the induction, what's very important? You use the induction hypothesis because up to k many terms, what can I do? I can use the result of the induction hypothesis. So left-hand side will be who? Left-hand side, it's going to come out as, what is it? That up to k many terms will be replaced by the induction hypothesis, which is a 1 minus cosine 2kx over 2 sine x. That's great, right? And then that's going to be added by what? The next term of the sequence. So that's the very typical skill that we need for proving the induction with the sequence and series, isn't it? And now I'm going to put it into the common denominator. Sure, why not? But you know, the reason I came up with this for the unholy problem is that to remind you of a very important formula often disregarded when you're working with the trigonometry, which is the factor formula. So here, I'm going to put it into the common denominator, so it's going to be 2, so let me just write in different color, plus 2, add 2 sine 2k plus 1 x sine x. So that is the identity that I have to simplify further, because the beautiful thing about the induction is that you already know the answer. What I mean by you already know the answer is that, you know, I already know the result of proof. So it needs to be the difference between the 1 and some bizarre expression of a cosine, but I got 1 minus cosine and the sine, I don't like it. But here's the thing, every time you see this product of a sine or cosine, it should really remind you the sum to product formula. So what do I mean by that? You know the sine compound is a sakokosa, and then the cosine compound is kokosasa, right? So among them, who has expression of consecutive sasa? That's the compound angle of a cosine, isn't it? So then you know cosine A minus B is co plus sasa. Can't be bothered, okay, to write all that. So let me just write it. And then if I duplicate this with the sum inside, you know it's gonna be negative outside. So I'm gonna replace that with the sum inside here. Then it's gonna come out as a minus. That's great. Okay, then in order to induce the product of a sine, what I'm going to do is subtract. You see? Then you get the twice of a sasa. That's great. And on the left-hand side, you see the difference of a cosine. And that is something to memorize, please. Okay? But you don't have to do this all the time. You can think intuitively. If I got, for example, twice of a cosa, that's likely to be the difference of the sine compound, because the sine has the sakokosa. But if you get the koko, then it's likely to work with the sum of the compound angle of a cosine, right? So like that is the way you're going to memorize. So this is going to be cosine A minus B minus cosine A plus B, right? Things like that. So that is something that you must memorize because it's very, very popular for trigonometry. So okay, so for this one then, using that sum to product formula, I know that this is going to be cosine minus the difference of the angle. So it's going to be 2kx, because that's 2k plus 1x minus x. And then in order to induce the sasa, I'm going to find the difference of the compound angle of a cosine. So I'm going to put minus cosine, the sum of the angles. So 2k plus 1 plus 1, so it makes it 2k plus 2x. So that's great. Well, I don't like this bracket. So let me put the x, and then the bracket here. So that's great. So that's the one that I can replace here, you see. So if you plug it in, who cancels out? Minus cosine 2kx, positive cosine 2kx cancels out. Now I subtracted it, so that one, So then I'm going to be only left with what? 1 minus cosine 2k plus 2x over 2 is what I've got. Sorry, over 2 sine x is what I've got. Oh yes, I want you to emphasize this really, really much. What do I emphasize? Not only the formula, but also induction. Induction is often 6 to 9 marks because they expect you to 3 steps. The basic step, proving induction hypothesis implies the result to prove, and also writing down the conclusion. Please write down the conclusion. You're going to say, since the basic step worked, and assuming induction hypothesis implied the result to prove the result was true. Therefore, by the principle of mathematical induction, the statement must be the true for the positive integer. You have to write down the conclusion. You cannot skip. Okay, and then for the trigonometric induction problem, yes, it's very often to use it for solving another equation. So let's use it. So if I do that, what you get here is, it's a 2 terms only, the sum. So it's going to be 1 minus cosine 4x over 2 sine x is equal to cosine x. But as you can see, if you rearrange, that's the 2 sine cosine, that's the doubling of a sine. So simpler the better always. So you're essentially solving this. However, you're absolutely right. Every time you're pairing the 1 with the positive 1, negative 1 with the cosine, it is really just to use the double angle. It is really to remind you to use the double angle of the cosine. So this is going to be 1 minus, I'm going to do 1 minus 2 cosine square of 2x, isn't it? Oh, sorry, sine. Oh, that's lovely. So that's going to cancel out. So it's going to be 2 sine square over 2x is equal to sine 2x. Oh, okay. Then I can simply divide, right? Because it's got the common factor. So I'm solving just sine 2x. Square is equal to, the square got cancelled out because I divided by sine 2x, which is common factor. And then 1 over 2, then I can solve the equation, right? No, please don't do this. Please don't do this because trigonometric function can often be 0. So I'm very reluctant to divide. You should always factorize upon the rearrangement. So what I'm going to do is a sine 2x. If I factorize, it's going to be 2 sine 2x minus 1 is equal to 0. So then you're solving for the new factor law. Either sine 2x being 0 or half is what you're solving. Okay? So that's great. Sure, so the question number 12 on the problem was something with the complex number and trigonometric induction, but it was inverse trig. It wasn't that bad because they were giving you a lot of identities. But for the trigonometric induction function with the right angle triangle, such as sine, cosine, tangent, it often very difficult because it uses the compound angle formula like that. Sum to product or product to sum. You must know those formula. It's not on the booklet. Okay? So I wanted to finish up this lesson by giving you a very nice another possible a paper 3 problem with the trigonometric induction. So if you Unholy, my friend, have a look at this, and this is a very nice problem because it uses something with the tangent. Most often the trigonometric induction problem on our papers has been always usually with the sine or cosine, but this year it hit the arctangent. That's interesting. But now I give you the one with the tangent where his argument seems to be working with the geometric series, and maybe you can find the pattern by playing around with some identity with the tangent function. Please have a look. Please have a go. It's a very, very nice problem. But yeah, that's pretty much it for me today. I know once I received the November paper, I was like, oh yeah, maybe I should do the review. I was watching some Unholy and then getting my business clean, and then I wanted to somehow associate with the, a bit more extended version of each question, because those questions could have been twisted in those ways. And I think this video, the purpose of this video was to, generally go over what to expect further, right, as a possible section B problem or paper 3 problem. So it's a very nice opportunity to go over those techniques with you. Okay. So that's pretty much it for me today. I will see you next time. See you.